So the piece of metal, now let me make a picture. Here's the piece of metal. It's actually you're going to do it once with aluminum and once with copper. Okay. So here's my piece of metal. It looks like this. And then here's his hand. I'm not a good artist. That's his hand.
Fingers going backwards. It looks like a bird. Yeah.
You know, hand. It had 5 fingers. I made sure I had 5. Okay, so the piece of metal was releasing energy, right? So the way we say it is that the energy flowed into his hand, okay? And that we designate that energy flow, the movement of energy, as Q. Okay, so this is the Q for the metal. Okay. And then there's a Q for his hand. So the Q for the metal plus the Q for his hand. So now the metal is releasing the energy. Its energy is going down. The energy for his hand is doing what? It's going up, right? Now, if that was the only two, so let's say the piece of metal in your hand were the only 2 things in the universe. I could say that equals 0. And that's the conservation of energy. And what this means is the energy that's lost by the metal, right, is equal but opposite to the energy gained by his hand. And that's conservation of energy. Conservation of energy. Okay, now. Now, is it the only 2? Is your hand and that piece of metal the only 2 things in your universe?
There's variables.
Yeah, there's a lot of stuff, right? So the number of Q's that go in there's a lot of them. All right. Now, so if I wanted to know how much energy left the metal, I would have to measure, right? I have to measure, if I wanted to know that, there's a couple ways I could do it. I could measure it directly somehow, or I could measure all the other stuff. Because this law of conservation of energy says that that's true, I could say Q of the metal, I'm going to say M, equals minus Q of the hand, right? And if I could measure this, then I automatically, I know what that is. Because it's just the opposite. And you said it, you knew it, right? The metal loses just as much energy as the hand gains. That's if those were the only 2 things in the universe, okay? This concept comes from what we know as the first law of thermodynamics. We don't cover that in this class. But somebody mentioned entropy. Was that you? Right? Entropy is the second law of thermodynamics. And then there's the third law of thermodynamics. And then after that, there's nothing. But this first 3 laws of thermodynamics. It's like I don't know if you guys ever read the robot series or anything, but the laws of robotics. Okay, at least get it from the public library as an audiobook. These are all books that, when I mention stuff, these are all things you should do in life, I think. This is my take on it.
Again what it was.
The Robot series by Isaac Asimov. It's an old series. Yeah, it's an oldie. Yeah, fun. They made a movie. You can watch the movie. I think there's a movie about it. iRobot?
Kind of follows that. It's not as in-depth.
Yeah, well, no movie ever is. Movies are always kind of a disappointment. Like the Harry Potter series. How many of you have not read Harry Potter? But watched the movies? No? Well, the movies are okay, but the books have so much more backstory. And the guy who reads them is really good. He's fun to listen to. Anyway, sorry. Yeah, I don't watch TV, so got to do something with my spare time. All right, so this is conservation of energy. Now, here's what we're going to do. I'm going to show you kind of how this experiment works. So, this is a very high-tech scientific piece of apparatus known as a coffee cup. Okay? And when you do this experiment, you're going to put some water in it. Now you're going to weigh it, you're going to put the water in it, you're going to weigh it again because you want to know how much water is in there. Okay? And then you're going to do this. Now, why do we use styrofoam cups with coffee? Insulates the heat, right? So in this problem, when we're doing conservation of energy, it helps to solve one of our problems. It eliminates everything in the universe except the cup. So we do have to take into account that we have a cup that absorbs some energy. But now, this conservation of energy statement, like if I could cut your hand off and put the piece of metal in there and put it in the cup, then it would only have one more thing over here, and that would be the calorimeter. This is called a calorimeter. Now what are calories? It's a unit of energy, right? So a calorimeter is a device for measuring energy. Okay? So this is what you do, though. You have the water in here. It's going to be at room temperature. You're going to come over here. You're going to I'm going to find the tongs. I don't know where they are. They're out somewhere. Austin is pretty awesome. Yeah, they're right there. You take a pair of tongs, you grab it, bring a paper towel, dab that water off. Not this. I do that to my kids all the time to embarrass them. Because if you don't stop doing that, I'm going to start doing it. Oh. You dab the water off. Well, you don't have to be clarifying. And then you're going to stick it in the calorimeter. You can put the lid on it, okay? And then you're going to watch the temperature change. So you'll know what it started at, and you'll watch to see where it ends. Now, when you do that, when it has water in it, it's a little more bottom heavy, so it won't flip over on you, unless you hit it. Okay, so let me rewrite this what we did, because right now it's not clear how you what we're doing, right? So let me explain to you. We want to know how much heat leaves the metal block. Okay, so I have a cup like this. And then a lid and a thermometer. And then I have this metal rod that may or may not fit very well in these cups. Some of them are pretty big, so I wouldn't grab the really tall ones. I'd grab the shorter ones when you do it. Okay? And what's going to happen? Well, energy is going to go from the rod to the water. Okay? So I'm going to have a Q for the metal rod, so I'm going to say R. Okay? Plus, I'm going to have Q for the water. Because the water's like your hand now. It's absorbing the energy. And I'm also going to have a Q for the calorimeter. Now, in an ideal world, actually, you can buy things like this that absorb almost no energy at all, and then we can assume that that number's 0. And for a lot of experiments, we do assume that it's close to 0 because the energy changes are large enough that it's not a big deal. But for us, we're going to be like we're going to be scientists. We're going to take into account all the little details, okay? But you can do this. This is something you can do at home, right? All right. So, what's all that going to equal? 0. And in reality, the calorimeter represents everything in the outside universe. Okay. Now, for now though, I'm going to ignore it, and I'll tell you how we take care of it. Okay. So now here's what we do. We say Q for the rod is equal to minus Q for the water, with a negative sign in front of it. And let's assume it's 0 for now. And then I'll do another one where it's not 0, and I'll tell you how you take care of it, okay? Okay. So I want to know how much heat leaves the rod, right? How am I going to do that? Measure the water.
Change.
All right. I was going to do this analogy, like where I take money out, and I'm not going to tell you how much money I have. I was going to hand everybody some money, and then I was going to ask you, how much money did I just give away? Because nobody saw how much money I had, but how would you figure it out?
I had
add up what everybody got, and then you would know how much money I lost. And that's basically what you're doing here. You're going to figure out how much energy the rod lost, right, based on how much energy the water gained. You just add it all up.
If you could measure it easier.
Yeah, of course, you know, when you hand out money like this, it might not turn out so well. So this is lunch money. It's not really lunch money. I ate my lunch already, unfortunately, because I didn't eat breakfast. But now I have my breakfast for my lunch, so it's okay. All right. So how am I going to do this? Well, it turns out there is something that saves us in all this. It's an equation, unfortunately. Okay. And we know that Q for water can be calculated. And there's we call it the MCAT equation. It's the mass of the water times the specific heat of water, and I'll tell you what that is in just a second, times its change in temperature. So think about, C is a constant, by the way, for water. It's remember we talked about physical properties? It's a physical property of water that's constant. Metals have specific heats. Insulation has specific heats. You have a specific heat, right? Everything has a specific heat. It's a physical property of whatever the thing is. Okay, now, let's forget that, though, for now. It's just a constant, and I'll explain to you what it is and what it looks like in a second. What do you think M stands for? It's mass. So we're going to put mass down here. What is it the mass of? Water. Now, this delta means change, okay? So that actually represents temperature change, and it's delta T is your final temperature minus your initial temperature. Okay. So let's say your temperature goes down. Okay, that number is going to be negative. If your temperature goes up, that number will be positive. Okay? So if I think about what I just said then. If I take the water and I measure the temperature before, and I throw the metal rod in. Now the metal rod's hot, right? What's going to happen to the temperature of the water? Temperature of the water is going to rise. Temperature of the metal rod is going to go down. Okay, but delta T for the water will be positive, and delta T for the rod will be negative because one's going up in temperature and one's going down in temperature. Now, so let's work through how we actually do this experiment, this part of the experiment, this calculation, right? You take this cup like this and you weigh it, and you put about 50 milliliters of water in it. This is for the second part of the experiment. I'm not talking about the first part yet. 50 mils of water in it. It's empty right now. And you weigh it, and you write down the mass. The difference in what it is when it's empty and what it is when it has water in it, okay, is this number. It's how much the water weighs inside the container. How am I going to get the temperature change? Well, I have a thermometer in it at the beginning, right? I have the water in it, and then I add the metal rod to it, and then the temperature goes up. This is not really supposed to be used to stir, but you can use it to stir a little bit, or you can do this. Don't do this. Why don't you do this? The heat from your hand. It's an insulated cup, but your hands might actually change the data, so you hold it like this. Try to be a little, keep your universe from going into their universe. And you're swirling this around, and this temperature is going to rise. Your initial temperature is where it started, right? Your final temperature is where it ended. Now, here's something that's interesting, okay? Or I think it's interesting. Over time, the metal rod and the water reach the same temperature, and the temperature stops changing. Differences in temperature is what drives the movement of heat energy through the system. So if you're hot and you go into a cool room, right? The temperature difference is what drives the loss of energy from your body and into the room. And vice versa, if you're cold and you go into a warm room, it's the temperature difference of your body and the outside temperature that drives temperature change, energy transfer to your body, okay? So eventually, when the two things come to the same temperature, energy stops moving in the system. We call this thermal equilibrium. At some point, both the rod and the water will come to the same temperature. So to check that out, then what that means is if you measure the temperature of the water at the end of the experiment, it's also equal to what? Temperature of the rod at the end of the experiment. Okay, so I'll talk about why that's important in a second. Okay, so look at this. This is a constant. That's the mass that you measure, and this is the change in temperature for the water. Since that's a constant, you can look it up. Okay, and I'll tell you what it is in just a second. It's one of those ones you should probably remember, but if you don't, it's okay because I'll give it to you. Okay. But you have everything you need to calculate this number. And then you just change the sign, and that's the energy change in the rod. So now you can calculate how much energy left the rod and went into the water because you measure everything about the water to get that. And it's the I gave you all a bunch of money. We can pretend I gave you money. And you counted it all up, and then you figured out how much money I lost by giving the money to you. Okay? Make sense? Okay, so what do we do with this data? There's a lot of things we can do with this data. The goal for today is to calculate the specific heat of the metal. You want to know what C for the metal is. So here's the problem that I'll pose to you then. Let's say you have C for the metal follows the same equation as C for water, okay? So what's the first thing that goes here? Mass, M. And it's going to be the mass of the metal. My gosh, how are you going to figure out the mass of the metal? Dry it off and weigh it. Yeah. Don't throw, it tells you to throw it back in there. Don't throw it back in there until you've weighed it. And this is a problem because they're all different. We use these as unknowns for another experiment for 1A. And so they're all a little bit different, so you won't be able to go back and get the mass correctly. Although, in the end, if you're really good at this, you can figure out which one it is by fudging the calculations a little bit. This is going to be C for the metal, and this is going to be delta T for the metal. Okay, so we know we can weigh it. In a problem, it'll just be given to you. Okay. Delta T for the metal. So this is a little trickier, but this is why you need to measure this temperature at the beginning of the experiment. The boiling water that you take it out of, and I'm not sure it's going to boil, to be honest with you. They don't seem like they're getting there. It's a pretty lame hot plates. But anyways, maybe it'll get there. When you pull it out, okay, of the water, remember thermal equilibrium? If you measure the temperature of the water, you know the temperature of the metal as long as you've given it enough time to stop changing temperature. So the initial temperature of the metal is whatever that water in that beaker is. So you stick a thermometer in it, you look at it for a while, right?
How long would you say it takes?
As long as it takes to stop changing. I don't know what that number is. Every thermometer is a little different, probably 30 seconds at the most. And that half a degree can make a difference in these kind of measurements. I'll talk about the specifics of measuring, but you need to measure to about the 1/10 of a degree or 2/10 of a degree if you can. That's about where you have to be at. Digital will lie to you. It'll tell you all kinds of other digits, but none of them may actually be true measurements. There may be measurement errors in there, okay? So your eyeball is, I think, just as good. So you're going to take the piece of metal out. The initial temperature for the metal, remember this is T final minus T initial. This is the temperature of the hot water. Sorry, this is the mass of the metal. This is, you have to weigh it. And we're looking for specific heat of the metal. Okay. So right now, if you wanted to solve that equation, what's the problem?
You don't have the constant.
You don't have the constant. That's what you're looking for, and you don't know this. Except, what did we just figure out? What was on the right? Q of the metal is opposite of the Q of the water. So you can figure out, based on the temperature change of water, how much energy left the metal. And you just take that number from this previous slide, right? Q of the water, because here you have everything you need here. I'm going to tell you what that number is, but you have everything you need here to do this part of the calculation. So you're going to try to put all that together today in the experiment. I'm going to add one more twist to it because we want to be scientists and do this right. Oh, I'm sorry. I want you to be scientists, so we're going to do this right. I don't know what you really want to do. I don't want to superimpose my feelings on top of you, but I think you're all scientists at heart. Okay. Questions about that so far? All right. So I'll come back to the specifics of the lab because we don't really do the calorimeter constant part, the measurement of the calorimeter, the extra Q that I just made 0 for now. We really don't do that in lecture, and really what I'm doing right now is covering lecture. Okay, I want to talk to you a little bit about what heat capacity is, or specific heat is. And here are some examples. Here's lead, right? You notice that specific heat is very low, 0.128. And same as gold.
That's interesting. 'Cause
But if you look at the specific heat units, it's the joules per gram degree Celsius change. It doesn't say change, but that's what that is. And the specific heat is the amount of energy that it takes to change the temperature of 1 gram of substance 1 degree. The energy it takes to change, right, the temperature of a substance, 1 gram of substance, 1 degree Celsius.
And that will give you that in joules. Is that right?
Well, I'll talk about that in a second. Change the temperature of 1 gram of substance by 1 degree Celsius. So if you had 1 gram of lead and you wanted to change its temperature by 1 degree Celsius, it would take 0.128 joules. If you wanted to do the same thing for water, right, it's over 10 times as much energy to change the temperature of water. Metals have very low heat capacities. In fact, compared to water, almost everything has a low heat capacity. That's kind of the crazy good thing about water. Like if you live, okay, so there's a guy named Joseph Black, and this goes back to like the 1600s, and he was in Scotland. And he wanted to know, why doesn't the temperature of Scotland vary very much during the year? Like it never gets super, super cold, and it never gets super, super hot. And it always falls within a certain range. And what he discovered was the idea that water has a very high specific heat. And the specific heat of water, when the weather turns cold, because Scotland is surrounded by an ocean, that water releases heat energy and keeps Scotland from getting too cold. There's probably some Scottish pride in all this, but. And then in the summer, when it got really hot, where other places were really hot, right? Scotland stayed fairly moderate. And I don't know if you've ever been there in the summer, but it's really cool. That's because the water around Scotland absorbs all that extra energy, and it makes for very moderate climates. Okay, San Francisco's the same way. Like, you've ever been to San Francisco? Oh yeah, it's going to be 78 today, low of 68. All right, very small range of temperatures, very moderate temperatures. Occasionally it goes up high, but right on the peninsula, right on the very end of it, it's always about the same temperature. Right? And that's because the ability of water to absorb energy and to release energy. All right, so this is that number that I was talking about. But for water, when this was originally done, this is when the calorie was conceived. This number, in calories, is just 1.000 calories per gram degree Celsius. And that's where this whole energy scale concept came up with originally, is with the calorie. And the specific heat of water, why not make water's like the most universal thing ever? Let's just make it 1, and so they made it 1. Right? And then the temperature scales all grew from there. All the energy scales all grew from there. Okay, so if I weighed 1,000 grams, which I don't, right? That's a kilogram. I always tell people my weight in kilograms because they never know what it is in pounds. They're like, oh, I don't know. It sounds like a small number, right? So if I weighed 1,000 grams and you wanted to raise my temperature 1 degree Celsius, right? I am mostly a bag of water, right? We know this. We're like 90% water or something like that. It would take 1,000 calories to change my temperature 1 degree. That's kind of what that means. Now, if I was something like lead, it would take 10 times less energy to change my temperature. So metals can have really large temperature swings, right? Things like water have very small temperature swings. So what you're going to see when you do this experiment, right? You're going to take this hot piece of metal, you're going to throw it in the cup with the water. The temperature of the metal is going to go from 100 degrees Celsius to very near room temperature again. But the water is only going to rise a few degrees up. And that's because of the difference in the specific heats of water and the metal. Now, when you build your house, okay, someday when you build your house, or if you've built a house, or you've lived in a house that's built, what do they put in the walls? Insulation, right? Insulation has a very high heat capacity because it's filled with air, and it's very hard to heat air up. Okay? It's very hard to get heat to transfer through air, I should say. So they put wood as the frame. Like your house, if you made your house out of metal, right, and the sun hit it, it takes so little energy for the metal to heat up. You would automatically, on the inside of your house where the beams came in, all those beams would be like 100 degrees right now. Right, so we use wood because wood, right, I don't see it here, but wood has a very high heat capacity somewhere here between ethanol and water. Okay. Ethanol, by the way, is like alcohol, drinking alcohol. I don't know why they put that one in the list all the time, but it seems to be interesting, so I'll just tell you that. All right. So on exams, you get those values, and you just have to use them in calculations. Okay. So going back to, I hope I can go back to. No, I can't get back to that thing yet, so I'll figure out how to do that later. Going back to what I was talking about before, when you need the specific heat of water, you can just use this value. Okay? And then you can use that in your calculations to get the specific heat of the metal. By the way, if you need the slide that defines it all, it's all right here. Okay? I'm not going to talk about it now. I've talked about it already in context. Okay, so you have a copper penny, all right, in the snow, and you pick it up. How much heat is absorbed by the penny as it warms from a temperature of the snow, minus 5 degrees Celsius, to the temperature of your body at 37 degrees Celsius? Assume the penny is pure copper, okay? and has a mass of 3.1 grams. You can find the heat capacity of copper in this table. So we're going to find the heat capacity and we'll write it down. What is it? 0.385. So let me go back to the thing and I'm going to write this down. And the units are joules per gram degrees Celsius. So we just want to know how much heat is absorbed by the penny, right? So I'm going to write this equation, Q for the penny is equal to the mass of the penny times C for copper. So I'm going to say Cu because Cu is a symbol that we use for copper, okay? Times the change in temperature of the penny. So now let's identify all our variables. This is the process that I want you to go through. I read, I looked at the thing that I need, and now we're going to identify, because we have an equation, we're going to identify all the variables. So I need the mass of the penny. What's the mass of the penny? 3.10 grams. The C for the copper I have, that's written over on the right side. I looked that up already. All right. Now what's delta T? Well, delta T is the final temperature minus the initial temperature. So what's my final temperature? Yep, it's your body temperature is 37 degrees Celsius. So this is delta T. And then minus the initial temperature, which is minus 5 degrees Celsius. Five zero or 550? Oh, minus 50 there. Sorry, I got it wrong. So what does that end up being? 42, right? So now all that's left for me to do the calculation is to plug everything into the equation. I found everything that I need, okay? If you're missing two things, you can't solve an equation. So that means you didn't look something up or you didn't read something in the problem, okay? So I'm going to say Q is equal to 3.85 grams. Actually, let me write that a little smaller because I'm going to run out of space that big. Q is equal to 3.85 grams.
3.10.
Oh, sorry, 3.10. Yeah, thank you. Get these numbers stuck in my head, and I can't get them out. And then the specific
That's where you
key,
get the
that's where they got the
3.85.
3.8. That's what I said. I get these numbers stuck in my head, and I can't get them out. 0.385 joules per gram degrees Celsius times the change in temperature, which is 42 degrees Celsius. Now what you'll notice is grams go away, degrees Celsius go away, and I'm left with joules. So all I have to do is find my calculator, plug those numbers in. And I get 50, which by the way is a very small number in terms of joules. 50.1 joules. It's 3 sig figs because everything in here has 3 sig figs based on my calculations. Okay? I'll let you worry about the details on that. Oops, sorry. Maybe I should have left that up for a second longer, huh? If I can get it to go up again. There we go. You guys got that? Okay, so 50.1 joules. All right, so this is just another variation. I'm just going to do some examples, variations of a same problem. The temperature of a lead fishing weight rises from 26 degrees Celsius to 38 degrees Celsius as it absorbs 11.3 joules of heat. Now, you knew it went up because if you're absorbing energy, your temperature has to go up. Your delta T is positive. These are all things that I think about as I'm reading the problem so I don't make mistakes. And they want to know what is the mass of the fishing weight in grams. So what I'm going to do is that sounds like a specific heat problem. I write out my equation. Okay. Anytime you hear joules and masses or changes in temperature, it's this equation. So Q is equal to MC delta T. And this is the Q for the lead, which is PB. And this is the mass of the lead and specific heat of the lead and the change of temperature of the lead. Now, before I get into all that, what am I solving for? What is the mass, right? So this is what I want to find. This is what I'm going to suggest to you guys. Solve your equation before you plug in your numbers. I think they tell you these things all the time, but I'm just going to tell you that. Sometimes I don't do it because I'm in a hurry and I can do it. But I'm going to solve for the mass, so that's just going to be Q divided by C delta T. Okay, so Q, they tell me 11.3 joules. Probably got measured in the calorimeter using water. Okay. Delta T is the final minus the initial. It's 38.0. No, just 38. Oh, we're not being very careful today. Minus 26. I'll get 2 sig figs out of it anyways. Let me just do that degrees Celsius. Oops. That's going to be 12? Yeah, it's a good day. I did some math. All right. What's missing?
The C.
C. What was it? You guys remember? We read it on the slide. 0.128. Yeah. So on that slide, now it doesn't tell you to look it up, but you know when you do the calculation and you're setting it all up, it's the thing you don't have, you're going to have to look it up. Or you're going to have to know it. If it's water, it's 1 in calories, or 4.184 in joules, okay? But I'll give it to you. If I forget, somebody tell me and I'll give it to you on a test. I mean to give it to you. So this is for lead. This is 0.128 joules per gram degrees Celsius. And so I can plug it all in and I can do my calculations. I'll cross out my units. Let me just write it all over here. M is equal to 11.3 joules. Divided by 0.128 joules per gram degrees Celsius. And then delta T is 12 degrees Celsius. You notice that here the degrees Celsius will cancel. The joules will cancel, and I have 1 over grams, so it ends up being grams. Okay? So I don't know what that number is, so I'm going to go plug it in my calculator, 11.3 divided by 0.128 and divided by 12. And I get 7.357 grams. Now, by the way, if you plug it into the equation like this and you have mass over here, it's going to come out to grams. So if you don't cancel the units because you're in a hurry, it's still going to work out. Just make sure the units that you plug in are all what they should be. Okay? The units are whatever are here in your specific heat. Okay. Sig figs? So there's 3 here. There's 3 here, but here there's only 2, so we got to go 2. So 7.4. When you take exams, just as a side note, sometimes there's 2 answers and one's the rounded version of the other. Right? They're not asking you just to do the calculation in those questions. They're asking you to assess sig figs. Not all the questions do that, but you got to test different things, and so that's one of the things that will happen sometimes on exams. Okay. Let's see, how much time do we have? I want to make sure you have time to do the experiment. Let me just double check to see what slides I have left. This is actually the last one. Yeah, we'll pass on this one. I'll work it out and give you guys the answer later. Let me go ahead and finish talking about the experiment now. Okay. So I already told you how to do the second part of the experiment, but we have to take into account what's called the calorimeter constant. Okay? That is, that this is not perfect in isolating the universe from you. Okay? So when I draw my calorimeter picture, I draw it like this. And I put my thermometer in the top, so there's my thermometer like this. Oops, I can just draw it in that little spot there. And then I have a piece of metal in there. So this is my thermometer. What we were talking about before is you actually have several components that you have to consider. And so you have the calorimeter. So we have, the metal. We have the Q for the water. And then we have the Q for the calorimeter. And all that equals 0. That's conservation energy. Now what we're going to do is we're going to take into account the Q for the calorimeter. We're going to figure out what it is. Okay? And the way that you do that is fairly simple. You put the thermometer in. You put in 50 mils of water, and it's cold. And you measure the temperature, okay? And you weigh it. So you put 50 mils of water in, you weigh it, you get the mass, put a thermometer in, you measure the temperature. You get a second calorimeter, okay, and you, coffee cup with a lid, right? And you put hot water in it. Now, I think they have you use hot plates and stuff. Now, see, these are weak. Not even boiling yet. I'm going to stick it on high. These are probably like safety for this classroom. The ones I have that I like to use the best will burn paper when you stick it on top. It lights on fire. They get really hot. That's hundreds and hundreds of degrees Celsius, or 500. Okay. Okay, so this is what we're going to use for hot water. Okay. I think they probably tell you, usually in labs they tell you to heat the water. We're just going to turn that on, get it to be hot. Everybody's going to have a slightly different temperature because of that. You capture 50 mils of water in a graduated cylinder. All right. Now, if you want the water to be as hot as possible, which is probably what you want to run this under the hot water for a while so that the glass heats up, because the glass has a specific heat too. And if you put hot water in it, because it's cold, it'll absorb energy from the water, and the water will be cold when you pour it into your coffee cup, okay? So you're going to heat this thing up. You're going to pour it into a calorimeter with a cap on it, just like the one up there, and measure the temperature of the hot water. Wait about 30 seconds to see what that temperature is. So This is crazy because I get to do this from back here. And then what you do is you add 50 mils of hot water. Okay. So once you've added the 50 mils of hot water, the equation for conservation of energy for this, okay, is Q for the hot plus Q for the cold plus Q for the calorimeter. That's equal to 0. So you notice those first two Qs? Those are based on water. So you can figure out all the information for these first two Qs because they're both based on water. And you know how hot, you know the hot water is going to cool down. You know the cold water is going to heat up, but it's still all going to can't come to the same final temperature. Okay? So that leaves the only thing that you don't have is this, the calorimeter constant, or the Q for the calorimeter. Okay, so that's what you're going to do in the first part of the experiment. Now, there's more calculations involved, but let's just review what you're doing in that first part, right? You're going to take cold water, put it in the cup, measure the temperature. You can be doing that while your lab partner is heating up some water. This is the first part of the experiment. You have weighed that water that's in there, okay? And then your partner is going to come over with the hot water and calorimeter, and then you're going to record the temperature right before you add it over. Okay? Now, when you pour it into the other one, put the lid on it, so you're back into your starting calorimeter, so don't mix them up. This is important, you don't mix it up. You could put a C on that one if you want, the one that you start with. And that's the one you're going to use for the whole experiment today. Cold water's in there, add the hot water, measure the final temperature, and then you weigh it. Because that difference, where it started to after you add the water, that's the mass of the hot water. Okay? So you have all the data for those two parts, the Q for the hot, the Q for the cold. You have the mass of the water for each just by weighing it. You end up weighing it 3 times. At the beginning before you put water, after you put the cold water, after you put the hot water. And then you have the temperatures because you measured the temperature before you added the hot water. You measure the temperature of the hot water, and then you mix them together and you measure that temperature again. So there's 3 temperatures that you're going to record. All you have left to do is figure out what Q for calorimeter is. And that is by you add those 2 things together. It's not going to be 0. Right? Change the sign, and that'll be the Q for the calorimeter. Okay, so now, Q for the calorimeter, there's a lot to keep track of, but you can ask questions while you're doing it. Q for the calorimeter is just going to be calculated as C delta T and you're actually going to calculate C for your calorimeter. Because the amount of energy that the calorimeter absorbs depends on the change in the temperature, just like anything else. We're not going to take into account the mass of the calorimeter because it doesn't change. So that C that's actually there is the mass times the specific heat of the calorimeter. Okay? Its units are just joules per degree Celsius. Now, the calorimeter had the cold water in it when it started that warmed up. So the change in temperature for the calorimeter is the same as the cold water. Okay, I'll say that. I'm just going to put the subscript here. The C here, that's a change in temperature for cold water. Now when you go up to do this calculation that's up here, right, you have this number. You can plug that in. You can plug that in, and that only leaves you this to calculate. And what you're going to use that number for is to calculate the specific heat of that metal. Okay? So, any questions? There's going to be lots as we go along. So, yeah. So, find a lab partner. It doesn't look crazy. right? And decide on what your roles are in the experiment, what you're going to be doing, right? And let's plan this out so we can get it done.